yesterday. Right. So again, let me go back to the last two reactions. So we talked about ways to convert alkenes into alcohols, and we talked about oxymercuration being one, and then we talked about hydroboration slash oxidation being the other, right? So on your flashcard for these two reactions, you need to get these reagents, because that way, that's how you're going to remember what's what. You can see here for oxymercuration, this is mercury, right? For hydroboration, this is BH3. And so that's how you'll be able to tell those two apart and know what they do, right? One of the keys to these reactions is actually learning the reagents and what they do. Let's go to, let's see. And if you watch the last video that I sent you, the mechanism for hydroboration was in there, right? And it shows, I want to show you why it's anti-Markovnikov without going through the whole mechanism, and then we'll go to a different reaction. All right, so a couple of things I want to talk about with hydroboration, and then we'll move on to another reaction. So let's talk about first, why is anti-Markovnikov, right? And is everybody okay with that terminology when I talk about Markovnikov and anti-Markovnikov, right? So when we say, let's say we have an unsymmetrical alkene like this, and we're going to add water to it, right? If the OH adds here to the more substituted carbon, then it's Markovnikov. If it adds to the least substituted carbon, then it's anti-Markovnikov, right? So I know that word itself is, everything is German, but I just want to make sure we understand that terminology. And this is, again, dealing with the regiochemistry. Right, because this is a region of the alkene, and that's also a region. We'll just say that's region 1. And those are the two locations where you can add an OH group. So that's why we call it regiochemistry. And that's what that Markovnikov and anti-Markovnikov describe, the regiochemistry of the reaction, like which carbon in that double bond is going to add the OH, which carbon is going to add the hydrogen. So the reason why hydroboration is anti-Markovnikov is actually quite simple. Right? Let's look at this same double bond. In this double bond, right, there's between these two carbons, this carbon right here is going to most likely be partially positive, right? This one is going to most likely be partially negative. The reason is because if I broke that carbon up by resonance, if I took the pi bond and shifted it, would the negative charge would prefer to be here on this carbon, right? Because this is secondary and that's primary. So we know that. We know the trends for negative charges, we know the trends for positive charges on carbon. And so with that in mind, this is the electronic nature of that pi bond or the double bond. Right, that's the electronic nature of the alkene. The more substituted side is more likely to be positive, because if you make it a cation, it's going to be more stable. The more negative, the less substituted side is more likely to be negative, because if you make it an anion, it's going to be stabilized. Right, so if we know that this is partially positive and that's partially negative, the boron, the BH3 bond is actually, there's a dipole towards hydrogen this way. So that hydrogen is actually partially negative and boron is partially positive. So this is why it's anti-Markovnikov, because when you hydroborate the bond, this is coming here, and this pair of electrons is coming. Say something right quick. This pair of electrons is coming here, like that. Right, so over here, I'm going to get this, where hydrogen is here, and boron is here. And then eventually, it's that boron is going to become an OH group. So the anti-Markovnikov regiochemistry stems from the electronic nature of the alkene and the electronic nature of the borane, right? BH3, when it lines up to insert into the alkene, it's going to line up based on those dipoles. So that's why we see what we see. That's why the OH always ends up on the least substituted carbon. The other thing about hydroboration is the stoichiometry, because this here, alkyl borane, right? I can add another alkene to that because I have 2 hydrogens left on there, right? And if you watch that video, you saw the fact that I can make that alkyl borane. It actually ends up with 3 groups on it before the second step, where you go in and you add the peroxide and the sodium hydroxide to convert those into alcohols, right? So a stoichiometry is for a hydroboration is usually 3 moles of alkene to 1 mole of borane, right? So it's always, that stoichiometry is always going to be 3 to 1, right? But we'll worry about that. We'll come back to that. Are any questions about anything? All right, let's pull some other examples from up here. I'm gonna leave this for you. Let's take, I'll cut this whole thing, and then we're gonna work the ones we know, and then the ones we don't know, we're gonna go through and talk about them. All right. Let me crop this out, and then I'll crop it down some. And then we're gonna work through the ones we already know. without the mechanism. All right, so let's take, let's start here. What will be the product if I took that alkene and I treated it with hydrogen gas and platinum? What type of reaction is that? What's the name of that reaction? Anybody? Okay, good. This is a hydrogenation. What does it do?
It turns it into an alkane.
So it takes that double bond and it adds a hydrogen to each side and turns the alkene to an alkane. So we added a hydrogen here. We added another one here. Good, excellent. All right, what about this reaction right here? What am I going to do there? And what's the name of it? So this is addition of HX, is that right? And we've seen that already. What happens here? What am I doing? I'm adding H to one side and Br to the other side, is that right? The question is, what is the regiochemistry? Because where the H goes and where the Br goes actually matters. And we learned that already. So what is the outcome of this reaction? Which carbon in the double bond is the most substituted? Let's start there. Because this is my double bond right here, is that right? Which carbon is more substituted? So this is one, this is the carbon, that's a carbon. The carbon on the left has two carbons bound to it. The carbon on the right has one carbon and a hydrogen bound to it. Which one is more substituted?
The one with two carbons.
The one on the left. So where is bromine going here? Because one thing we know about this particular reaction is that this will be the intermediate. Right? You're going to have an intermediate carbocation for this reaction. We know that because the alkene is going to act as a nucleophile and attack the hydrogen on HBr, and then you end up with a carbocation intermediate, and this is where the H is right here that got picked up. So the bromine ends up on the more substituted side. That's why I wrote here regiochemistry as a question. What type of regiochemistry does this follow?
Markovnikov.
Good. So it's Markovnikov. Excellent. All right. What about here? This is another reaction that we should be familiar with at this point. What are we going to get? And tell me one special characteristic about this reaction and the name of it. I'm adding Br2. I'm adding a halogen to the alkene. What's the name of that reaction?
Halogenation.
Okay. Tell me something about halogenation that you know about the product. that always is true about halogenation? What do we know about how the halogens add? Are they on the same side or are they always on opposite sides? That's what I'm trying to get at.
They're on opposite sides.
Always, right? So I'm gonna put this here on a dash. I'm gonna put this one here on a wedge. Anytime we add Br2 to an alkene, I'm adding a bromine to each side. And they have to be, what do we call it when they're opposite like that? What's the term we use for that?
Trans.
Trans. Have to be trans. All right, always trans. What about here? What reaction is this? I have BH3 in the first step, and the second step, hydrogen peroxide and sodium hydroxide. What reaction is that? All right, anytime you see this, followed by that, it's a hydroboration oxidation. Anytime you see that. What does that do? That reaction. What do we use that reaction to do to an alkene? What did it do up here to this alkene? What functional group did it convert that alkene into? Didn't it convert it into an alcohol? With anti-Markovnikov regiochemistry, meaning the OH is on the least substituted carbon and the H is on the most substituted carbon. So let's go back. What's the product going to look like? Where's the OH going to be? And where's the H going to be for this in this example? Anybody? Which carbon is least substituted? We just did that.
The one on the right.
This one. Right? So the OH is going to be there. I need to move that. I'll just erase it and redraw it. The OH is going to be on that carbon. Right there. And the H is going to be on the carbon next to it. All right. Anybody not following that? I'm telling you, you got to make some flashcards and you got to look at these reactions every day. That's the only way they're going to stick. All right. Questions? Any questions about anything?
So on hydroboration, are they on the opposite? Because like why are they on the opposite side compared to the
You mean how I have it drawn?
yeah.
That's been pointed out. Yeah, it's just symmetrical. I could have drawn them up, but
Oh, okay.
it's just a preference. But that brings up a good question, because one of the things about this reaction is that the OH and H will always add to the same face. They'll never be trans, right? They always add in what we call a syn fashion, where the OH and the H are always on the same side. That's a great question, though. But I could have drawn it. I think you're asking why didn't I draw it like that? Is that right?
Yeah, you answered
Yeah.
my question.
Yeah, it doesn't change anything. All right. The only reaction we haven't seen before is this one, MCPBA, and followed by some acid, some type of acid source. So we're going to look at that reaction. I'm going to cut this out. And we're going to look at that separately. I want to use that like that. Let's see. No, I'll just rewrite it. So if I have this alkene and I treat it with, this is a totally separate set of reagents. Now this is MCPBA. First step, second step, I'm just going to add some H plus, right? This set of reagents does what we call epoxidation. And epoxide is a special type of ether. If you remember from when we studied functional groups, we studied ethers and we studied esters and all types of stuff, right? So an epoxide is a special type of ether. So it's a 3-membered ether. So this is what the product is going to look like. We're going to go through the mechanism. Right, so this 3-membered ring right here, that's what we call an epoxide. Right, that 3-membered ring, we call that an epoxide. All right, there's another way to do this, which is to use hydrogen peroxide and sodium hydroxide. Right, you get the same outcome. The difference is this is for more electron poor. Alkenes, right? So if you have an alkene that's electron poor, you'll use this method. Again, every reaction that we learn is a tool. Every reaction that we learn is a tool for organic chemists to use to achieve a certain end. Like what am I trying to do? I'm trying to make epoxides. I need a method. So every one of these methods has some specificity to it, right? If it's electron poor, then I need to use an electron rich epoxidizing agent. If it's electron rich, then I need to use an electron poor epoxidizing agent. Right. So in this case, this alkene would be considered electron rich because it's tri-substituted. So we can use MCPBA. Let's see how this works. If you watch, I think I sent the epoxidation video yesterday. We're going to go through the mechanism. Again, everything that we're looking at is nucleophile and electrophile chemistry or acid-base chemistry. That's why we spent so much time learning about how to push arrows and how to use curved arrows and what that means and what is a nucleophile, what is an electrophile, right? And electrons flowing from source to sink. That's exactly why we went through all of that first before we got to these reactions. So with the mechanism, let me show you how this works. So this is my alkene, which is going to be my nucleophile. And then MCPBA looks like this. So it has an aromatic ring. Well, let me draw it the other way. Right? Let me draw it out so you can see it. It's a peroxy acid. So it looks like this. And there's a chlorine on it. So this is MCPBA, metachloroperbenzoic acid. So this is the part you can see right here. That's where my oxygen is going to come from. Right. So the way that this works, let me see if I can. Is the alkene is going to actually attack one of the oxygens. And then I'm going to make a bond between hydrogen and oxygen. And I'm going to end up making a bond between each carbon and oxygen. All right, so let's look at that. I gotta move this down. So I'm gonna attack here, like so. And then I'm gonna take a pair of electrons from here. This pair of electrons is gonna come here, like that. And then this pair is gonna pick up that proton. It's a little bit convoluted, but you can see from here, this is where my two bonds to oxygen are gonna come from. Right, so the alkene attacks oxygen, and then the OH bond, those electrons are used to make that other bond to oxygen. And then you break the OO bond, which is a fairly weak bond anyway. So you're gonna break that, and you're gonna make a pi bond here, and then you break this pi bond and use that to pick up, do proton transfer. So it's all happening at the same time. Well, what do we call it when everything happens at the same time? What type of mechanism is that?
Concerted.
Concerted, good. It's a concerted mechanism. So we end up with this plus this. Right. So that epoxide, that's a really, really, really important functional group. You'll be surprised how many natural products that have biological activity actually have epoxides in them, especially a lot of like your anti-cancer natural products that are derived from like sponges and derived from different types of biological sources. A lot of them have epoxides incorporated. And low key, it's a pretty robust functional group. Even though that 3-member ring is really strained, it's not trivial to pop it open. Right? You got to do it under really facile conditions, like the conditions have to be right. Otherwise, that ring is pretty sturdy. It can withstand a lot. All right. Any questions about the epoxidation? I need to make that bigger. Any questions about this? Right. And if you watch the epoxidation video, the mechanism is there. All right. This is for MCPBA. I think that mechanism is in there for sure. It's called like a butterfly mechanism or something like that. All right. So we've gone through this reaction wheel and we looked at, I'm gonna go ahead and write in what this is. That's an epoxidation. And this is the product here. Right, so every one of these reactions is a tool. If I want epoxides, I have ways to make them. If I want alkyl halides, I have ways to make them. If I want alkanes, I have a way to make it. If I want alcohols, but I want it with anti-Markovnikov regiochemistry, I have a way to make it. If I want a halogen, a dihalide, I have everything I'm making. All I'm showing you is that I can take an alkene and convert it into multiple different functional groups based on what I use to do the reaction. All right, questions? Any questions? We'll pause right here. How many of you, I can't see your hands, but you can unmute. How many of you have already started making flashcards? So that means nobody. So we need to get popping on that. I'm telling you, that's the best way for this section. That's the best way to approach it. Make flashcards and look at them every day. Every day. All right, let's see. Where are we now? Yeah, let's talk about this right here too, because we can talk about epoxide opening real quick, and then that'll probably be the last thing we talk about today. I'll just add it to this page. All right, so this is dependent also on when you open an epoxide, it's going to depend on the conditions. So under acidic conditions or neutral conditions. If you do it under acidic conditions, the epoxide is going to open at the most substituted side. Right, or it's going to open at the most substituted site. If you do it under neutral conditions, it's going to open at the least substituted site. All right, so let's take an epoxide, a basic one. So I'm just going to use this one that came from this reaction right here. All right. Now, if I take this and I treat it with acid and then treat it with some nucleophile, let's say methyl sulfide. All right. That's going to give me a product. If I just treat it with methyl sulfide by itself, that's going to give me a different product. This will be considered under neutral conditions. And then this is acidic. Right, so let's look at the products first, and then we can explain why. So with the neutral, under neutral conditions, this is gonna actually just pop this open. So this is gonna attack here and pop that open. So this is, let me just say that too. That's one. And then two, I'm gonna have to add some H plus. Because this is, when you open an epoxide, generally what you're doing is making an alcohol. So after when you pop it open, you're going to get this. And then the SCH3 is here. And then eventually you'll just treat it with an acid to do proton transfer. So you'll have this. Like that. Right, so under neutral conditions, you just again attack the more substituted side, pop it open, and then quench it at the end. That's what the H plus is for, just to do a proton transfer to neutralize that oxygen. If you do it in the reverse by adding the acid first, you're going to get a totally different outcome, right? So your alcohol is going to end up, and I'll show you why. So your OH is going to end up here. And then the nucleophile you added in is here. You can see the difference. What do we call that? Where I got either side I can attack. And what's the term we use for that? What's the term we used up top? Either both of those carbons in that epoxide represent a region. So what do we call it when we see the two different products like that? So it's the same idea of regiochemistry. Both carbons are reactive, so I can attack one side or the other side. So either region. So it's different regiochemistry. So let me show you the acidic mechanism. So under acidic conditions, let's keep doing that. I'm going to treat this with acid first, right? So I'm going to add in H plus, and I'm going to do a proton transfer. So then I'm going to end up with an intermediate like that. The way to think about this is if I were to open the intermediate before the nucleophile added, which side is most likely to be positive? And how do I know? When we think about a carbocation, so let me say this part right here. So this would be considered secondary, and this will be primary. Which of those two carbons is more stable as a carbocation?
Secondary.
secondary. So if I pop this open, it's more likely to open on that side. So then I would have a plus charge here and then OH like that, right? And then my nucleophile can now come in and attack that. That's why the regiochemistry is different, because the side that's more likely to be a carbocation is the side that's going to get attacked, right? Because if I have a more substituted carbon and I get to this intermediate right here, right? That ring, I can pop that ring open and that carbon is more likely to be positive, right? So, and so that's why we see that regiochemistry under acidic conditions. All right, any questions about that? All right, I'm actually going to stop here. We only got 2 minutes, and I don't want to push you off the edge of a cliff. And yeah, so I'm gonna stop here. Any questions about anything?
For the reactions that we went over,
Mhm.
I know we went over the mechanisms of like 2. Do we need to know the mechanisms of the other like 3 or 4, or just like the final product?
Well, we went over actually oxymercuration, addition of HX, halogenation. We just went over epoxidation and epoxide opening. The only mechanism we didn't do was the hydroboration, I think, osmolation and hydrogenation. We haven't done those. But for the ones that we have gone over, I would say yes. You may not know the entire mechanism for every single reaction, but if I gave you, let's say if I gave you a reaction and gave you the pieces, you should be able to put the arrows in.
Okay, I got you.
You understand what I'm saying? So if I gave you all the steps and asked you to supply the arrows for each step, you should be able to do that. If that makes sense.
Yeah, it does. I got you.
Okay, all right, no problem. All right, any other questions? Make your flashcards, please. I promise you, they'll save your life. No other questions?